Okay, we're going to look at 5.6. I believe it's number 4. Oh, accidentally just clicked off. 5.6, number 5. So it's the parachutist. It's the one where obviously the parachute, you can see from my picture, I've already got it started with our given and find and picture and whatnot. Now, one thing you haven't seen me be doing in energy when I talk about conservation of energy is very many force diagrams, and they always help, okay? You should do more force diagrams than less. If you do an entire assignment and most of your stuff does not have a force diagram on it, you've probably done something wrong. Now, energy, you can kind of get away with that, but probably doesn't work on very many other things. Let's see it here. All right, so person is dropping out of the air. Okay, they start from 1 kilometer. They have a mass of 50 kilograms, and it says when they hit the ground, they have a velocity of 5 meters per second. Okay, I want to try and make sure I don't miss anything here. Jumps out of an airplane. All right, so yeah, that's it. Now we're going to assume that the speed at the top is 0. They weren't moving, and then they were, and yeah, that's where their energy comes from. So you have 2 ways to potentially do this problem. I'm going to do it the first way. Actually, both are going to go be really quick compared to each other. But the first way is something that you would have had to have done before learning kind of that method we talked about the other day that kind of changes conservation of energy. But I'll show that practiced a little bit here. Okay. If I do a force diagram on this person in general, I know there's force gravity and I know there's force friction. Now the size of these is a little bit weird because that is going to change throughout this process. There's going to be more friction in some spots, less in others. So I'm not so much worried about the amounts as I am just the fact that they are there. So before you actually saw that the other day, you would have had to use the work net kinetic energy theorem. Why? Because this only works when work is done by conservative forces, aka gravity and elastic. In this case, we can see that as the person is moving down, positive work is going to be done by gravity, but negative work is going to be done by friction, which means that guy's out. Now we do conservation of, the work net kinetic energy theorem. This is going to be work of gravity plus work of friction equals kinetic energy final minus kinetic energy initial. Now, one thing that I hadn't addressed yet is kind of the weird question that is asked in this particular problem. This problem asks the question, by what amount was the jumper's mechanical energy reduced due to air friction during this jump? Now, that sounds super scientific-y and whatever. What is that really asking? How much energy was reduced? How much energy was changed? What's the change in energy because of friction? In other words, that's asking, what is the work done by friction? And we can see that guy right there. Now, of course, work of anything can be calculated by force of friction times displacement times cosine theta. And we do know the displacement. We do know that it starts off 1,000 meters or 1 kilometer up in the air. But as I talked about before, friction is a little bit challenging on this particular front because it's not fair to say it's at a constant velocity the entire time. So instead, we're just going to leave work of friction here. The kinetic energy initial is simply going to be 0, because like I said, they're not moving to begin with. And now we can just kind of move this around. I'm going to move work of gravity to the other side. Kf minus work of gravity. And we'll fill in. What's kinetic final? 1/2 times mass times velocity final squared minus the force of gravity. Let's just go to mg, because we have m right there. Mg times displacement times cosine theta of gravity. Okay, 1/2, mass is 50 kilograms. The velocity final at the end was told us to be 5 meters per second. That would be squared, minus 50 kilograms. By the way, you would notice that there's 2 masses here, and you might say, why don't they cancel? But you'll notice I did not draw this over here, assuming that's work of friction. So they don't cancel because there's not one in every term across both sides. It has to be on both sides. So if I divided everything by mass, I'd have to divide this by mass, which kind of defeats the purpose of me trying to find what work of friction is. 50 kilograms times g times the displacement is 1,000 meters. And now the angle. Remember, this is the angle between the force and the displacement. Force of gravity is going down. The person is traveling down, so the angle should be 0, and that should be cosine of 0, so 1, leaving us with that guy right there. All right, now let's go ahead and plug in. We get 1/2 times 50 times 5 squared minus 50 times 9.8 times 1,000. And I get negative 4,000. Actually, let's just round this. It is 489,000. I'm just going to go ahead and round to 490,000 joules. Now, why does it make sense that that's negative? Well, the work of friction should be taking energy out of the person. Obviously, that's kind of the point of a parachute. You want to take that energy away, because if you don't take that energy away, all that gravitational, if you don't do work by friction, is going into kinetic, which is not a great idea to hit the ground with all of the energy from gravity over in kinetic. It's not going to end well. So this is how much energy was taken out of that particular situation. So that's our answer to part, I guess, A. There weren't really parts for this. The next question after that is, what is the average force of friction? Now, I told you that we don't exactly know what friction is doing here, and that's true, but we can still get the average. How can we do that? Well, you know how earlier I said we could calculate those force friction times displacement times cosine theta, but we didn't know friction? Well, we're just going to use that again. Work of friction is equal to force of friction times displacement times cosine theta of friction. And to find the force friction, we just divide those two underneath. This angle, by the way, since the object is going down and friction is going up, would be 180, making that -1. So we have force of friction should equal work of friction over displacement, let's go, times -1. And that would be negative 490,000 rather, joules divided by displacement of 1,000 meters times -1. And we should always get a positive magnitude in this particular case. So just divide by -1,000, and we get that the average force is 490 newtons, because it's a force. Now, I told you I was going to show you the other way just real quick. Hang on 2 seconds. It's not going to take me that long. I'm not going to go through all of this work again, but you can, in fact, use this guy now if we add this part in. Conservation of mechanical energy works if you put that work of non-conservative up there. Remember, that's going to be taking that energy out. So what is this? Well, that's all the types of energy that are changing. So I have gravitational initial plus kinetic initial. I'm going to ignore elastic right now. What are the work of non-conservative forces? Well, you come over here and you see which are my non-conservative forces doing work. Gravity, that's conservative. I don't have to worry about that. Friction, yep, that's the only one. So I'm going to go work of friction, and that's equal to gravitational final plus kinetic final. Once again, kinetic initial would cancel because it's not moving at the beginning, and gravitational final will cancel because it hits the ground at the very end. That is assuming, of course, I made the ground 0, but that kind of makes sense. And once again, work friction. That's what we're trying to find right there. In that first part, we could subtract that over. If you find that to be easier, it's going to work the exact same way. It's going to get you the exact same answer. You should, once again, end up with a negative number right there. And then you could come down to the second part, and you'd have to do that exactly the same as you did the first one. That's how you do number 5 on 5.6.